Hello, welcome to another Cosmology talk. This week we have Simon Birrer, a postdoc at Stanford. He's here today to talk about TD Cosmo, who just last week had a very, very interesting paper show up on the archive. TD Cosmo are one of the groups measuring H0 at the moment, and they do it by a strong lensing time delay. He'll go probably into detail about exactly how they do that. But for me, at least, the predecessor to TD Cosmo, holy cow, was the experiment that caused me to stop and actually take this H0 tension very, very seriously. Previously, it had just been a kind of conflict between Cepheid-based measurements and Planck, and you could just imagine that the Cepheid-based measurements had some sort of mistake, some sort of systematic error. But as soon as holy cow showed up with a completely independent measurement, also measuring a large value, it was like, wow, this is something to take seriously. So last week's paper was extremely interesting and basically threw the cat amongst the pigeons, and Simon will go into a lot more detail, but they basically relaxed a few assumptions, which widened the error bars. That's totally understandable. But then when they added new data to add the information in that they'd lost by relaxing their assumptions, their measured value dropped. It didn't drop quite to the level of Planck being 67. I think it dropped to about 69, but that's very, very interesting, because if I go back to the pre-holy cow days of not being that interested in H0, if they're now giving a value that's consistent with Planck, maybe I should be interested in H0. But Simon's probably going to have a lot more thoughts on this, so I'll let him do the explaining and we'll see what it looks like at the end. Thanks, Simon, for joining us. Do you want to briefly tell us about your work?
Yes, thanks for having me, Sean. So this quick summary is indeed extraordinary claim require extraordinary evidence. And so in this paper, we drastically relaxed assumptions that we previously made on the mass profiles in particular. And what we then did is, as you said, relaxing the assumption leads to wider error bars. That's the natural thing to expect. And then in a second step, we added an external data set. So this is not identical to the actual lenses that we measure the time delays on. And make the assumption that these are self-similar to the lenses where we actually need these profiles to be constrained. And then folded in this information, and we get an updated measurement of H0, which within the error moved down. And so the current measurement does not allow to say, is there a tension or is there not with these error bars? The key that I want people to take with when reading this measurement or the paper is not the numbers themselves, but the methodology and the possibility to add new data. So this is really the first time where we experimented with adding external data to constrain mass profiles. And so there is a huge potential how we can utilize this type of framework to move forward.
So I normally ask for two simple things for people to take away from the paper. You've given one. Do you have another simple one? I mean, I'm sure people will take the numbers away, but you can try hard to stop us with your two simple things.
Yes. So another takeaway is, do the measurements blind in regard of H0, make the data open source and accessible. So they're tough and hard measurements. There are certain assumptions and choices that go into those. And one of them is what data do you use to constrain certain aspects. And to not become biased to what you want to get out of it, it's really important to have this. And that's what we've done in the past with the previous measurements. That's what we've done in this one, and that's how we move forward as well.
Yeah. I can't stress how much I also support you're doing the blinding, especially with something like H0 where the stakes are so high, right? It could be Nobel Prize worthy if it turns out to be some genuine new physics, and it would be so easy for you guys in the experimental groups to just, I don't know, not even consciously do it, but just be like always kind of thinking, well, it must be in the low to mid 70s. So where's the systematic error? We have to fix this. But if you blind yourselves, you don't know which way you're pushing yourselves. So it's just so important.
Yeah, it's hard, and sometimes it's uncomfortable, but that's what it should be.
Yeah. I mean, because exactly, if you unblind yourselves and then you've got a result like the one now, or even a more crazy one, maybe you unblinded yourselves and it would have been 80 kilometers per second per megaparsec.
That was always a possibility for every single measure.
Whereas if you'd done that before checking all the errors, you'd be like 80. No, something has gone wrong. I have to fix this. So yeah, now do you want to go into some more detail into the background? Obviously, why H0 is interesting maybe doesn't need any introduction, but why strong lensing time delay, and why was this specific problem the one that you've relaxed the assumptions on?
So here, slide in a nutshell, time delay cosmography. So what you see here on the right is a quadruply lensed quasar, where you see 4 point sources embedded in a host galaxy that forms this nice Einstein ring. And when the photons travel through the universe and reach the detector here, the Hubble Space Telescope, they have different light travel time depending on which image we observe or the photon has traveled through. And so there's a path difference between, say, the top and the bottom image. And so this is a time delay that occurs for photons that have been emitted at the same time. And this time delay is related to how the bending happens at the lens, the deflection. And that's the crucial part for the Hubble constant, the distances involved in this problem. So the longer distances you have, the longer you expect this delay to be. So these are few days to few months. The longest is about 110 days in the current sample that we have. On clusters, it's even years. And so here, this is effectively the equation that I have. Here, this is the time delay that you expect from the curved path of the photons, has some absolute distances where these numbers here are angular diameter distance from the observers to the deflector, from us to the source, and from the deflector to the source. So effectively these scales here involved. This is the quantity we want to constrain. And these are geometric quantities describing the deflector itself.
So obviously there's no letter H in this equation as you've written it, but obviously the H is hiding inside the distances, right? Because if the expansion rate was bigger or smaller, then the things would be closer or further away at the same redshift.
Exactly. So all the H0 measurements are effectively distance measures. And then you fold in the redshifts and you get the expansion. That's the background of the techniques. Here you see an animation of the flickering of the quasar on the right. And if you then do every night cadence, you monitor the brightness, you can get a time delay being measured due to this variability. If we just have standard galaxy lenses that are not variable, we're not measuring a time delay, even though it's present in every single one. So this is then the TD Cosmo project that you mentioned. It consists of formerly known Holy Cow collaboration that has analyzed 6 lenses in great detail that resulted in 2.3% measurement of the Hubble constant. And it also consists of the STRIDES project. This is a dark energy survey affiliated project, finding lenses in the dark energy survey. It consists of the SHARP project, which is a program using Keck adaptive optics imaging to replace Hubble Space Telescope imaging, and CosmoGrail, which is the large program in monitoring lenses. So this TD Cosmo brand encompasses all these projects and their PIs. Here is a montage of the 6 beautiful images from Hubble Space Telescope, or at least this is an adaptive optics image from Keck itself. So what goes into getting an H0 or an absolute distance of a single lens? So what we have is high resolution imaging. Here, this is an example from a paper I wrote about 1-2 years ago. I also want to highlight all the other work on the other lenses that have been done with our collaboration. So high resolution imaging allows us to measure and describe in detail the distortion of the lensing effect that's going on, not just from the multiple images, but in particular of the shape of the extended source. So this is the imaging that we learn about the lens model. Then here is the time delay measurements. Then another ingredient is stellar kinematics. So this will then become a key anchor in the work that I've led. And the stellar kinematics is of the deflector galaxy, in this case, these lenses, to learn about the lensing potential from effectively the dispersion of how stars move in this potential. And what we also need to know is the line of sight contribution. So these lenses are not living just in a flat background metric. So the metric is distorted due to structure very nearby and along the line of sight. And we have to correct for these so that we are actually, when we're quoting a Hubble constant, we are effectively quoting the distances corrected to be the background metric of our cosmology. And then this data set, we can multiply its likelihood and do the inference. And here just highlight what the role between imaging and kinematics is.
And so just to be a slightly silly theorist and make sure I'm understanding correctly, the telescope that's taking the high resolution image that can give you the stellar kinematics is necessarily a different telescope to the one that's giving you the time delay? Because in one of them, you want to look for ages at one point, and the other one you want to be looking for tiny amounts of time to get the time variation. Is that right?
Yes. So all these figures are different telescopes and sometimes even multiple ones. The spectra, we have different requirements. This can be Keck adaptive optics. Here, this is Hubble Space Telescope imaging. Here we have super wide field and deep imaging or dark energy survey. And here we have 2-meter class telescope that we have more availability to shoot on the targets on a nightly basis. So the entire project involves a lot of diverse observational capabilities to actually do it. And that is now, and this is even more in the future, the case. It's not that it's $1 billion project, not at all. So it's comparably cheap, but requires a lot of different observational capabilities that we have to write all of the proposals for. So here's some, in that sense, forward modeling in action. This is work led by Anwar Shachib at UCLA. It's an example of how we reconstruct the lensing phenomena from the imaging data. So here we have one band of Hubble Space Telescope imaging, and here is a model out of it. And so we go on the pixel level reconstruction, and we call it lens modeling. So we propose a lens and the surface brightness and effectively simulate it on the pixel level. And so this was the summary last year. This is a paper, Wong et al., the latest holy cow results. Here, the set of 6 lenses that go in, where you have here overlaid the individual H0 constraints for each individual lens. These are the color ones. And the combined, on the likelihood level, combined constraints on H0. So a few things. So one is they're all statistically consistent with each other. So they can be drawn from the same underlying distribution. There's no indication that error bars or random error bars are underestimated. And all of those, except the first lens that have been analyzed, were done blind. So yeah, as you said, could have been 100, could have been 50. If the time delays were off, if some other things were dramatically off, this would have been the outcome.
So this is not information you've presented here, but it's just information I remember, possibly from this actual Wong et al. 2019. But there seemed to be a trend with redshift of these H0 measurements. I don't know if I'm looking at the data too carefully, because the error bars on the individual measurements are obviously quite large. But if I remember correctly, the 68.9 was slightly further away and the 81.1 was slightly closer, and there seemed to be sort of a trend. Is that something that I'm just like seeing patterns in the noise, or is that something that maybe is worth keeping an eye on?
It can be both. With the 7th lens that I'm just adding here, the tension in that sense dropped to, I think, something like 1.6, 1.8 sigma. What do you call that? I mean, it can be a sign of underlying systematics or just a statistical fluke in the specific direction of parameters that you look. So if you have 20 parameters that you correlate one of each other, you get phenomena like this. And that also underlines that we need to go to larger samples. And then you will pop up trend will either be confirmed or come back. So this leads me to this figure. So this is half of the figure that is in the recent paper, which summarized the previous results. So this is the Wong et al. Results that you show. And the lenses are modeled with power loss and in parallel being modeled with NFW profiles and a constant mass to light based on the visible light that we see from the deflector. So it is we call a composite. So these 2 profiles have been run. They still have of order 7 to 9 free parameters that we fit and constrain. And if you split and say you trust one model more or the other, and that's been done in the Millen et al. Paper, the TD Cosmo 1, where we effectively run the inference of the 7 lenses either with one family of model or the other, we get very consistent results. Another question is, do these assumptions matter? And if so, how can we further constrain it? So why did I do the work? This is known under the umbrella of mass sheet degeneracy. So these are different density profiles that have some transforms that scale that we call the mass sheet transform. They look by eye different. Here's in log scale. And the Hubble constant that comes out of the different lines are each of them different by 10%. And imaging data alone does not allow you to distinguish among these different profiles. It's a specific transform that leaves the imaging observables invariant. And that is the crucial aspect. So no matter how sharp your images is, imaging data is not allowing to distinguish among these types of transforms.
When you say imaging, do you mean the image of the thing being lensed or the image of the lens itself?
Of the things being lensed, of the arc, of the positions of the quasar, all the type of information in the distortion.
That's true even if you had like a optically perfect down to the photon image.
Yes, at one point you can say if you can resolve a star and its surface, then you can have an absolute calibrator of the size of a star. So if you have an absolute calibrator of how large your actual source is, you can break the degeneracy. And so you can now put priors on what are the profile shape. You can put in priors of what the source scales are. What we did in this exercise, we allowed the full degrees of freedom of this transform to be as likely as any other one. So the outcome could have been any of those transform or even more crazy ones. And so this problem is known since decades. Here I listed some older and younger literature that say there may or may not be a problem. And so the summary here of the paper is effectively we moved from having assumptions and data to having assumptions and data. Well, we relaxed significantly the assumptions and added more data to the problem in terms of how the mass profiles look like. And the data that we added is effectively summarized here. So this is a velocity dispersion or effectively predicted velocity dispersion for different values of this lambda c. So different scales of how the profile has been transformed. And the good thing is the velocity dispersion is actually changing under these transforms. So if we very well measure the potential that has the imprints in the stellar motion.
And this is of the lens itself.
Of the lens itself, we can break it and thus can say is something more like 0.8 or 1.1. In that sense, I remove previous assumptions and say, I don't trust it, or let's see what's happening if we don't need to run it. And now the question is, how can we measure velocity dispersions very well? And the sad thing is, in that sense, per individual lens, we have not a very precise handle on it. But the key comes with the numbers. And so what we added here is a sample of SLACS lenses. Here's a montage of those, where we have excellent imaging from Hubble Space Telescope and kinematics from Bose spectra. And so in that sense, come back, why did I do it is, I was not convinced fully for making big claims about new physics, whether the assumptions are viable or not.
So these assumptions were a power law density profile or an NFW profile with the mass light being...
Yes, an NFW plus a constant mass to light. So you can think of like the dark matter and the stellar components together.
And the reason why those assumptions are believable in the first place, that comes from hydrodynamical simulations, is that correct? Or
more like n-bodies predict NFW profiles, and the other is like what are possible like mass to light gradients, or how much do you think stellar light tracing baryonic matter. In this work here, we're using hydrodynamical simulation to validate our approach. These hydrodynamic simulations may not resemble, or actually statistically do not resemble, the actual real universe. This is not a surprise. There's moving lengths, there's still numerics in there that does not go to the percent level yet. But the complexity that is in there, these profiles are not power laws or not whatever we think they are parameterized. And our approach could be verified on those. So when we apply this mass sheet transform on top of the models that has been previously submitted blindly actually in this challenge, and folding in the velocity dispersion that has been self-consistently being computed out of the hydrodynamics, we actually get a consistent answer there. That's reassuring that the methodology we have is doing good enough on the hydrodynamical simulation. That's effectively the story behind it, and maybe just move on how we actually use it. And here's effectively the data set that's in the paper, that when you add the SLACS lenses, here we have velocity dispersions, and we have the measurements, that's the data where the fibers have been placed on the galaxies, and here the prediction from our joint analysis.
Mm-hmm. And you are able to do that prediction via looking at the actual lensed image and then make the prediction?
Yes, so there are different things that go into the prediction. We know what is the light profile of these galaxies from looking at the images, or measure its half-light radius. When looking at the Einstein radius of it, so we're doing the modeling of the lenses basically the same way as we do it on the TD Cosmo sample. So we have the same information content. And on top of it comes whether there is an additional mass sheet transform on top of the model family that we're using. So we're using the same model family for the TD Cosmo lenses as for these SLACS lenses, and then apply effectively hierarchically an overall shift of the profile. What if all the profiles are a bit more fluffy? What are all the profiles a bit more costly? And so here you just see qualitatively the difference. So this is in the paper for our inference of TD Cosmo plus SLACS. What is our average profile? Slightly transformed, where this corresponds to the power law. This is one of the two model families we previously used. And here we compare two model predictions with lambda int equals 1, which is effectively the power law period. And here a lambda int of 0.91, this is the median value that came out of this analysis with the SLACS. And I mean, you see some, the model predictions is slightly off. And the set of 33 lenses makes the difference. It's not one or two lenses.
So the SLACS is somehow preferring a bit more of a bulge, less density at the center and more density away from the center.
Yes.
Okay.
And now the question is the SLACS lenses, are they self-similar enough to the TD Cosmo lenses? So what we wish to have is effectively an exactly identical lenses or galaxies that are indistinguishable any other metrics. That's not what we currently have. The hope is, and in the future we're gonna have, like Rubin Observatory, Euclid will find thousands of lenses. And so there will be a lot more lenses that may be very self-similar in their nature to the ones where we actually have the time delays.
Is there any reason to suspect that the TD Cosmo and the SLACS samples are not statistically similar? Is there like a bias in the selection of either of them that one might?
So I wouldn't say there is a reason to assume prior to doing the analysis that they're different. I mean, the formation channels of elliptical galaxies follow certain physics and merger histories through cosmic time. There's some selection effects in terms of how often you get a quad versus a double, so how spherical the lens is. And so that caused a bit of a selection effect in terms of how elliptical actually the lens itself is. So there's certain details that are different. And also the redshifts are slightly different. And thus you probe a bit a different physical scale when you have the same Einstein radius of, say, 1 or 2 arc seconds. And so some of those we mitigated with specific parameterization that allow a trend to follow, that the data can constrain if there were. And so far in the data set we don't see any further trends that pop up in the metrics that we looked while it was blind. But it's definitely more now that we have these results to look into what is the tailored data set that we can use to actually rule out any of these differences or confirm them or whatever.
I was just wondering two things, I guess, about the details of the actual modeling. What is going into obtaining these yellow data points? And what's stopping you measuring all of the TD Cosmo lenses with as much accuracy as these purple points for the SLACS ones?
We actually have them more accurate than the purple points here. They're just only 7. So in there, it's the number. And another part that is different, in that sense easier on lenses that don't have quasars, is when you take a spectra, you need very high signal to noise and very pure spectra to measure the velocity dispersion is effectively an absorption line width in the spectra. And so contaminations either from skylines ruin it. And one contamination you have when you look at quasars lenses is the quasar. So you have a very bright quasar nearby of the galaxy. Sometimes it's like an arc second away or even closer, that is outshining in photons, the actual signal that you want. And that is going to be tricky. So you need adaptive optics supported spectral measurement to filter the photons that you want to look at. While for these lenses here, you don't have a quasar outshining the elliptical galaxy. And I can go back to these ones. You see it's challenging and really requires 10-meter class telescopes to get these dispersion measurements.
So on that plot where you had the predicted and measured dispersions, are the TD Cosmo ones on this plot, or are these just the SLACS ones?
Oh, these are only the SLACS one. Good question. In the paper, we have in a separate plot the ones for the TD Cosmo. This is the plot that I show you right before for the SLACS ones. And here is the data for the TD Cosmo in terms of velocity dispersion, where you see sometimes multiple same names. This means there are different measurements, different spectrographs pointing at the same lens.
I guess you don't see any kind of over or under prediction trend.
No, if there were overall under prediction, the model would have chosen a different mass sheet transform to compensate.
I just thought it might have chosen the different transform to compensate for the SLACS ones and then have a net bias on TD Cosmo.
Got it. No, so there is no inconsistency in the inference between TD Cosmo only and adding SLACS. So they're statistically consistent in that case between the blue, this is TD Cosmo only, and the darker purple ones, which is the full data set of SLACS. It's within the expected range. So when we did this blind, the expectation was the error will be 5% within 10%.
The other question I was going to ask was just like, if there was more detail you could go into about, like, at the moment, I don't have a good grasp of what this lambda parameter is for the actual parameterizing of the mass sheet degeneracy, and also like how you're actually doing the modeling. Like if someone gives you the kinematic data, how are you using that to actually make the prediction?
For the velocity dispersion, so there is what the prediction requires. Also, what you do is genes modeling. So we're solving the genes equation. We're making assumption that we're solving it in the spherical case. So currently we don't put in triaxiality. So here this is the genes equation. That is a relation between the potential, the gradient of the potential, and the velocity dispersion that is there. And in the modeling, so we're making assumption of, okay, what is the potential, the profile of the potential, and the profile of its tracer particles. And tracer particle in that sense is the stellar density. And so we solve those. The good thing is when you apply a mass sheet transform, you can get an analytical change of the prediction that you previously have to a very good approximation. And so in entire modeling, so it's solving this equation, and then what we need to do effectively that's in these lines is you have to compute all the observational conditions. So we know we're having a certain aperture that we take the spectra, so it's not a point estimate. The telescope has a point spread function, so we need to convolve. And so this is effectively a forward modeling of the spectra that we expect within the aperture and seeing conditions that we have. And so far, it's mainly single aperture. And there's one crucial assumption that goes into it is effectively the anisotropy, the radial anisotropy of the stellar orbits. So everything we measure is in projection. And depends on how the orbits of the stars move, they're more radially, tangentially, we get a different projected dispersion for the same underlying potential. And this is known as the mass anisotropy degeneracy, which is something that is to worry when you use velocity dispersion to constrain the mass sheet degeneracy. And so we have to simultaneously marginalize over the uncertainty of this anisotropy, which effectively is here. And anisotropy constraints we can derive from integral field unit observation. So if you have spatially resolved kinematics, then we know, okay, how is the trend, the gradient of the dispersion with radius? And then you can compare that with the profiles that you inferred from the lensing. And from there, you can say how much anisotropy or change in anisotropy there needs to be. And that we fold in. So we have, in the paper, we have 9 IFU lenses or 9 SLACS lenses have IFU data from VMOS that we're using to do so. And so when we go back to these contours, this A ani is effectively in the parameterized form that we're using in the anisotropy profile. This is the parameter that we care. So what is the radius where things from isotropic turns into radial anisotropy? And you see that there's a degeneracy between A ani and this lambda int.
Yeah, and so lambda int is the mass sheet degeneracy parameter. Can you maybe try and give me some intuition about what is changing as I change lambda? I guess you showed that density plot and you could see the bulge kind of happening for different values of lambda, but why is there that freedom? Like, why is the lensing not changing as I change that?
So what the mass sheet degeneracy does, so this is effectively the standard lens equation. It's wherever you see something on the sky is theta, and then you deflect it by an angle alpha, and it gets to some other coordinate beta, which is the source. And what you can now do is multiply both sides of this equation. And that's just one way to multiply it, is to extend it. So if you multiply by lambda, you can have an alternative interpretation in terms of their convergence or the projected mass. And so you have a transform profile that has the same, or the previous profile multiplied by a factor lambda, which lambda can be 1 or 0.5 or any other number, and compensating by a constant sheet of mass on top. And so this constant sheet of mass effectively does, it's not physical. It's not that on the entire universe you can put in a sheet of mass. But this effectively focuses or defocuses the entire light rays, so to speak. And so this additional focusing, for example, you can just make the source a bit smaller and you get the same image. And that is one way to look at it. And that's hence the name mass sheet degeneracy. You can put in a sheet of mass, rescale your previous model, and all the differentials, the relative differentials, relative size on the left to the right, relative magnification from the top image to the bottom image, they all remain unchanged.
And by assuming a NFW or power law, you're obviously picking a value of lambda essentially, because only one will fit that particular profile.
There's still a lot of degrees of freedoms, but not exactly in this direction of the mass sheet transform. And so effectively you break the mass sheet degeneracy by your specific assumed mass profile. Had we chosen a parameterization that is infinitely flexible, all our MCMC inference would have picked up the mass sheet.
And then this equation on the right, can you give an intuitive idea of why this addition or subtraction of a math sheet causes a linear kind of proportional change in H0?
Yes, roughly. So effectively the path, so when you change the scale, the source size, you effectively also scale where the light rays go. And so the relative path differences do also scale. Or one way is also that if you put in a positive sheet of mass, you need less actual lensing mass and hence less potential to do the actual curving at the lens itself. So you have a less, basically the potential well is less steep, and hence you have less of an additional time delay difference. What I have more is look in the future. So this is in that sense, the current state is like, okay, what's doing next? And I see, as I mentioned in the beginning, this is effectively a paper that removes a lot of assumptions, but it lays also the groundwork for how we can add more data to it. And that's my key here. And so how do we move on to solve this? The comments that I have is don't be too desperate about whatever the value is now. have ways to move forward, and it may end up here, it may end up over here. I don't really care as long as it's going in the right direction, whatever the Hubble constant is. So one way to move forward is on the actual time delay lenses, we can collect more data. And one is spatially resolved stellar kinematics. It's hard, but it's doable with VLT Muse, Keck, KCWI. And that's one way to, from here, move forward to shrink the error on the TD Cosmo only. So another one is improving kinematics measurement and modeling itself. So in the measurement of the kinematics, we need to assume stellar templates, so star formation rate histories, what is the composition. There's a lot we can do there to make this more reliable and mitigates current systematics that we have. And among all, increase sample size of time delay lenses. Here's just some illustration of currently that the team found, so that Strides collaboration discovered new lenses, and we already followed them up with Hubble Space Telescope. And not only that, here on this side, you have already a model of the lens. So we're actively working in increasing the sample size. So that's on the time delay lenses of what we can do and what we are doing right now. And the other way forward is adding external data sets. So I talked about the 33 SLACS lenses that fell into this analysis. So we can focus on finding and selecting for follow-up lenses that do exactly or as good as possible mimic the TD Cosmo lenses. In case there is systematics there, we want to nail it. And we can increase the sample size. So we expect 10,000s of lenses being discovered. It doesn't mean that all of them will be suitable or we need extra information and follow-up, but there is a lot in the future that we can do on this. And something that hasn't really been mentioned in the paper, but definitely we're going to do is there's a lot of kinematics of local galaxies that we have very high resolution, high signal to noise, spatially resolved. So from Sauron, Atlas 3D, massive projects that have a lot of studies of what is the internal kinematic structure of these galaxies. And it's all information we can use with some assumptions, meaning how are these local galaxies are similar to the redshift 0.5 galaxies. But it's all things we can do. And last but not least, way free, challenge yourself in moving forward. Improve simulation products for better validation. So full ray tracing. So we have, first time we had some hydrodynamical simulation for validations, and we learned a lot. And blind analysis challenges, it's a great way to get involved new people and old people in challenging ourselves on mock data products. Keep the analysis blind. It really helps in a discussion on the focusing of what's important, and whatever comes out, we're publishing. And so don't blame my future me if I give a different talk in 1 year.
When you say keep analysis blind, you mean like you unblind yourself? I mean, essentially what you guys have done, you unblind yourself, you have the holy cow results, and then when you want to analyze a new systematic, you kind of get someone else to reblind the data by just adding something that you don't know about, so that when you're doing your new analysis, it's kind of blind again.
So in this work, we used blinded products from the old analysis. So we didn't change anything that's in the previous TD Cosmo analysis of just the constraints we had from there. Mm-hmm. But all the other choices were done blind in regard to H0. For example, what data set do we include? What model parameterizations we do? And there we only assessed trends among parameters that do not directly impact our H0 inference. So lambda int, I exactly know when it's 0.9 or 1.1 what the Hubble constants are.
Right, yeah, that's what I was wondering about.
We set it, we just plot everything at 1 and just look at relative differences. And yeah, open source, there I emphasize that a lot. So all the software and code you can install and run the notebooks yourself if you want. And you may find, different options, different priors, different data sets to incorporate, and things may stay the same or wiggle around. I'm optimistic that within a year, we can get back down to something like 3% uncertainty.
So, okay, I have one final question I ask everyone, but I'm going to torture you as I've tortured other people working directly on H0 with a much more difficult question. Much less fun for you and fun for everyone else. And obviously you don't have the answer, because if you did have the answer, you would be writing a paper saying the answer. But what do you suspect the resolution to the H0 issue will turn out to be?
I only care what the real number of H0 is.
Oh, so you don't care from the theoretical side what might be causing it?
So yes, I do. And I haven't seen something that is very convincing for me for a theoretical side. But I have also to acknowledge that lambda CDM itself is not satisfying for me from a theoretical side. So there's a lot we don't know that is more fundamental than just say we have two numbers for dark energy, one for dark energy and one for dark matter. And this may be a window to look into what's going on. And so I'm keeping motivated to look into this and what is the age of the universe, where are we coming from and where are we going to? So I really see a real value of a direct measurement of the Hubble constant, regardless of whether this is now leading to new physics directly, or maybe someone in 20, 30 years can relate back to it and say, you know, that's what you've done and that's what I've learned eventually from it. So
outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
I'm very interested in all the things that are going on with black holes and the gravitational waves. I think this is really a new window that's now, and a few years ago that was like 0, then it was 1, and now we're already talking about measuring the Hubble constant, getting physics of neutron stars and etc. It's mind blowing how fast this field's evolving from that side. From a theoretical point, I don't know what space and time is.
Okay.
I think that is fundamentally what is going on there. We don't have a unified model, a concept to explain this.
You mean from like the quantum level? Because on the classical level, we kind of know what it is. Yes. It's a differentiable manifold.
Or just conceptual level. It may not even be quantum, but you know, so.
Oh, but I mean, at the general relativity level, isn't it quite straightforward? It's a differentiable manifold that curves under the influence of mass. Okay.
Yes. Yeah. Within one or the other framework, it's operationally doable. Yeah.
But yeah, what the graviton particle is certainly unknown.
Yeah. It's not my field, but it's something that I watch and see. We have so big mysteries in terms of what dark matter and dark energy are. What is the Big Bang and the flatness problem and so on. And maybe they meet somewhere with questions of quantum gravity. I don't know. It's just, I'm open-minded, and what I can do here is conducting an experiment and getting on the bottom of what the Hubble constant is. So
I guess dark matter has quite a few compelling models. Dark energy less so, and inflation, I don't know, some models are compelling, some less compelling for solving things like the flatness problem. It always has its initial condition problem of how to get inflation started in the first place. Awesome. Cool. Well, thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified, and click like to help with YouTube algorithms, and share the channel with your colleagues. If you have any questions or suggestions, leave a comment. While you're here, you can watch another video. Perhaps the best one will be last week's video by Ben Giblin, because he talked about in a little more detail how kind of one goes from the telescope measurements to data. And I think Simon mentioned a thing called a point spread function, which Ben went into some detail about. So if when Simon mentioned it, you didn't know what it was, watch Ben's talk and you'll then understand what it is. And yeah, thanks again, Simon, for the great talk.
Pleasure. Thank you, Sean.